Good morning, everyone, and welcome to today's Go Fly Master Lecture. To kick things off, I'll pass it over to Gwen Leiter, CEO and founder of Go Fly Prize. Gwen?
Thanks, Paul. Hello, everyone. So glad that you are joining us. As you all know, GoFly's grand sponsor is Boeing, and we are supported by not only Boeing, but our corporate sponsor, Pratt & Whitney, and our in-kind sponsors as well, who provide free and discounted software services and products to all of our GoFly teams. In addition, we are joined by our organizational partners. Last week, we were actually at EAA and AirVenture in Oshkosh, and we are joined by EAA as well as our other organizational partners. And today, we have a very exciting master lecture for you. We will be hearing from Dr. Akif Bolukbasi, who is a senior technical fellow at Boeing. He is an internationally recognized expert in aircraft crash safety and impact dynamics. Dr. Bolukbasi's technical knowledge spans multiple disciplines, including structures and materials, dynamics, biomechanics, test and evaluation, subsystem design and integration, information technology, and computational methods. He was a program manager and a principal investigator for over 20 IR&D, CR&D, and IAD projects. He was also instrumental in technology transition from R&D activities into Boeing products and is an accomplished author, presenting over 20 technical papers at industry conferences, and he has been published in several industry journals. Dr. Bolukbasi was one of the founding engineers of Simula Inc., a small technology company specializing in aircraft structural crashworthiness and ballistic armor. And he has been recognized for many accolades, including the AHS Jensen Award in 2011. And he has served as the technical chairman of the 62nd AHS Forum and currently serves as an advisory board member of ASU Mechanical and Aerospace Engineering Department. So without further ado, we are so pleased to welcome Dr. Akif Bolukbasi.
Thank you, Gwen. So in today's lecture, I will talk about aircraft crashworthiness. What are some of the issues? What are some of the technology solutions that we have? And hopefully give you some insight into how to design personal flying vehicles that are safe in terms of crash dynamics and mishaps. The lecture will cover the general principles of aircraft crashworthiness, but I will try to focus more on the applications to personal flying vehicles. So the definition of crashworthiness is the ability of the aircraft, including its subsystems, really to protect the occupants in survivable crash events from any injury. The key word is survivable because obviously some crashes are so severe that no matter what you do from a technology solution, they will not be survivable. Those things like aircraft breaking up in flight and those kind of things are very difficult to protect. But it turns out most of the crashes are survivable, and we have some tools to make the aircraft and particularly the occupants survive those crashes. So the crashworthiness capability is required in general terms. First of all, you have to provide some level of protective shell around the occupants. In other words, if the aircraft and the structure around the occupants totally fail and eliminate that livable area, of course, the survival for the occupants become very, very difficult. The other area is we have fairly large, what I call high mass items and cargo that if they come loose in a crash situation, they could also be very hazardous to the occupants. The examples for the high mass items obviously include things like engines and transmissions and rotor systems or any cargo that the aircraft carries. So the idea here is we want to be able to reduce the accelerations and the loads experienced by the occupants to human tolerable levels. It turns out that the human body has some levels of tolerance depending on different directions for the accelerations and the loads, and we want to make sure that our design keeps the loads and the accelerations experienced by the occupants below those levels. And I do have some slides later on to give you an idea of what they are and what direction we are most susceptible to injuries. And last but not least, in case of post-crash fires, this is after the aircraft has crashed and you might have fuel leaking, you have hot surfaces, ignition sources. You want to be able to avoid or at least delay post-crash fires, primarily to enable the occupants to safely egress from the aircraft. Now, recognizing that some of the personal vehicles have electric architectures, in those cases, of course, I will talk about this in a moment, we also want to make sure that the batteries or there is no electrocution hazards that are created. So that's an area in terms of the power sources that we have to deal with. There are a lot of design requirements and guidelines that have been developed over the years. The ones for the military rotorcraft are primarily in Mil Standard 1290, which is sort of an overall standard that covers various features for crashworthiness, and then it has sub-references to other specifications for subsystems that are part of the aircraft. And to go with that set of requirements, the Army has also published a crash survival design guide. This is a very good handy reference material for those who would like to understand a little bit on how to design things for optimizing crashworthiness. On the civil side, we have the FARs. The FARs, Part 25, of course, is for large transport fixed-wing aircraft, 27 and 29 for rotorcraft, and 23 for general aviation aircraft. And then, of course, the FAA also publishes advisory circulars on how to comply with the civil requirements that are in FARs, much like the military requirements that are in Mil Standard 1290. So in order to understand, how to protect occupants in crashes, we have to kind of think about some of the crash impact scenarios. And I sort of broke that up into two areas: vertical impacts, where you have a predominantly vertical impact velocity, and longitudinal crash impacts, where you have a very large forward velocity. So this is like a run-on landing crash scenario. In most crashes, of course, you never get a perfectly vertical or longitudinal crash. It's usually a combination of the two. In some cases, if the aircraft is yawed, for example, you might also get some lateral impact. But by and large, by segregating these into two areas, we can come up with design features that provide protection for those kind of scenarios. So on the vertical crash impacts, if you look at the acceleration versus time history, the first flat portion here is typically associated with the aircraft hitting the ground, and then the landing gear starts to stroke at a fairly low load. That's typically between 2 to 5 Gs, depending on the aircraft. And then after the landing gear is totally stroked and the aircraft belly hits the ground, we typically get a fairly large acceleration in the order of 40 to 50 Gs, which brings the aircraft to stop. But 40 Gs or 50 Gs is a very high acceleration loading for human tolerance. So we have crashworthy seats that tend to clip this at around 12 to 14 Gs, which are in the human tolerance level to avoid spinal injuries. So in the case of a vertical impact, which by the way are the most severe ones to protect against, we are depending on a series of subsystems, including the landing gears, the seats, crushing of the aircraft belly structure, as well as retaining the mass items to bring the aircraft safely to stop and not injure the occupants. In the case of longitudinal crash impacts, typically what happens is when the aircraft hits the ground with a fairly high longitudinal velocity, first of all, it tries to skid on the ground, but depending on the type of surface, you might get some, for example, if it's on soil, you might get some plowing effect where the aircraft starts to dig up the dirt and then decelerate itself. So you typically have a fairly low acceleration level, just like in the vertical case, associated with the initial impact and sliding. But then as you do plowing into the soil, you generate a fairly large longitudinal acceleration, which sort of slows down the aircraft a great deal. And then after that, it sort of slides out at a fairly low acceleration. So those are typically the acceleration time profile for longitudinal crash impacts and the vertical crash impacts. Now, in case of very large aircraft, like the fixed-wing transport aircraft, in addition to this effect, depending on the impact surface, and if it's, for example, if it's a hillside, you might also get breakup of the fuselage structure. So for rotorcraft, then the most important subsystems for protecting the occupants, particularly for vertical crash impacts, which are the most challenging ones, we have crashworthy seats that allow the seat to stroke at a certain load level, typically between 12 to 14 and a half. We have fairly high energy landing gears that help to slow down the aircraft. Now, we also have additional energy absorbing systems that are typically deployable. Those are called the external airbags, which I think are not only they are important for rotorcraft, but I think they're going to be very important for personal flying vehicles. And then we have crashworthy fuel systems that eliminate fuel spills and post-crash fires. And then last but not least, we also do design features on the belly of our helicopters using crushable structures. These are sort of sacrificial crushable structures that provide some energy absorption to limit the vertical accelerations that I showed in the previous slide. So some of those subsystems, like large aircraft structures, very heavy landing gears, those kind of subsystems may not be available or may not be at that scale for personal flying vehicles. So I think if you want to think about the crash safety of personal flying vehicles, you really should think in terms of a more occupant-centric approach. In other words, the focus is really just building a cocoon, if you can, around the occupant to protect them from crash injuries. Unlike for other systems or large aircraft where you have lots of structure to worry about, you can have large landing gears, which you may not have on the personal flying vehicles. So the most, in my opinion, the most appropriate crashworthy systems for personal flying vehicles, you obviously have some kind of seats. This could be a separate seat, or it could be a part of the personal flying vehicle itself, a tubular structure with hopefully some restraint system, and where the restraint system is anchored to where the occupant is sitting. I would also think in terms of helmets, because as I will describe in a moment, head injuries are one of the injury mechanisms that you have to provide against. And then last but not least is some kind of a deployable energy absorbing system, such as airbags. I think airbags can be relatively lightweight and they can be deployed upon impact. And if you position them in a way that they can provide a safety net or a cocoon, if you will, around the occupants. On the last bullet, I sort of alluded to this earlier. If the primary propulsion is electric driven, then we have to be cognizant of hazards due to battery fires or electrocution of the occupant at the end of the crash impact. So even if you don't have jet fuel to worry about, there are still power-related hazards that need to be considered. So this is a quick overview of human tolerance to impact. And the reason I have this slide is to make really two major points. One is that the human body, it turns out, has a much higher tolerance to longitudinal accelerations than it is to vertical accelerations. So the human body can withstand 40, 50 Gs in the longitudinal direction, of course, if they are properly restrained. But in the vertical direction, if you go over 12 to 14 Gs, you do start getting spinal injuries. The lumbar spine in particular is very susceptible to injuries, and that could be a problem. The other injury to really consider is the head impacts. And if this is typically head impacting some nearby structures, and this happens if the occupant is not properly restrained, or if you have structures so close that even if it was restrained, its likelihood of a head impact is very high. So to protect for those, you need to have helmets. There are a lot of different injury criteria that are used in rotorcraft in particular, and some of this have come from the automotive world, but some of it is fairly unique to the aircraft business. And the ones that I would emphasize, first is called the I-band criteria. In fact, it's what these two curves are. Basically, the I-band criteria is set up such that the human body can withstand high accelerations for very short periods of time, like a few milliseconds. If you subject the human body to accelerations longer than that period, as the duration increases, so does the probability of injury. But it turns out that based on the I-band curve, the vertical accelerations have an injury threshold much lower, typically less than 20 Gs, compared to the longitudinal accelerations, which tend to be in the 30, 40 Gs. The other injury criteria, this is again primarily from the automotive world, is the head injury criteria, and this basically is computed based on head accelerations, and it's an integral of the head accelerations. But what drives it is if you hit your head against a nearby structure during the crash. The commercial requirements, the civil requirements, FAA is primarily based on lumbar spine load. So in the test dummies, in the anthropometric test dummies, we can have load cells that measure the spinal loads, and there's a threshold that you should not exceed. This is about 1,500 pounds for a 50th percentile occupant. Dynamic response index and SI, the severity index, are not very widely used, but these are some of the criteria. Certainly the dynamic response index came from the Air Force associated with their occupant accelerations due to the ejection seats. So there are a variety of seat designs in the aircraft. And really, the idea here is to make sure that, first of all, the seat is retained in the original position in the aircraft in the crash, so the seat doesn't come loose from the airframe. And if that happens, then of course, there's no way really to protect the occupant. But also, in order to deal particularly with the high vertical accelerations, seats do provide an integral means of load attenuation in the vertical direction. This is typically associated with an energy-absorbing device that we provide that basically clips the 40, 50 G level acceleration down to more occupant survivable 12 to 14 Gs. The two seats on the top are typically what we call the crew seats. So these are fairly elaborate seats that require a lot of adjustment capabilities as well as attachment to the aircraft, whether it's attached to the floor or to some bulkhead. The two at the lower end are troop seats or the cabin seats. These are typically much lighter weight and they are tubular structures. In some cases, the place where the occupant sits is nothing more than a fabric or, it's like a hammock that the occupant sits in. So in my opinion, for the personal flying vehicles, these type of designs are probably more feasible in terms of providing a tubular structure and some kind of a cushion or a fabric structure to support the occupant. But even in that scenario, you still have to provide a restraint system. So the restraint systems obviously should be comfortable, otherwise people are not going to voluntarily wear them. And they of course have to be lightweight. They need to have what we call a single point release system. So if you look at this configuration here, you have two shoulder belts, two lap belts, and a tie-down strap. And all of these go into what we call a rotary buckle. And there is a release system here so that when the occupant twists this handle, it disengages all 5 lead points that come into that buckle. But you have to make that design such that it shouldn't be obviously inadvertently released. There are a lot of restraint system manufacturers, both for aircraft seats and also, this is also very prevalent obviously in cars and mostly also in the car racing industry. They have very sophisticated restraint systems that can be adopted to the personal flying vehicles. The other constraint, of course, is you can't just provide restraint in one direction. The occupant has to be properly restrained if you get a longitudinal, vertical, or a lateral crash impact, so it stays within the aircraft and then doesn't flail too far out to create a secondary impact with the aircraft interior. The webbing itself has to be, of course, wide enough to provide some, to distribute the loads evenly onto the occupant, both on the torso and also in the pelvic areas. And then the material for the restraint system is typically polyester. There are some restraint systems that are nylon, but the nylon stretches a lot more than polyester. So the better solution would be a low elongation polyester system that not only reduces the displacement of the occupant, but as you displace more, sometimes you get into what's called a dynamic overshoot condition that actually amplifies the loads on the seats. So to develop the seats and to qualify them, you have to go through a number of dynamic tests, and these dynamic tests essentially represent the two scenarios that I've discussed earlier. Test 1, which is shown here. This is typically done in a drop tower where you raise a seat fixture with the seat attached into some height that's required to create the impact velocity and then simply drop it onto an impact surface. So because of the seat's orientation, this particular test creates a forward and a downward load relative to the seat. And the type of acceleration pulses are typically given by, excuse me, a triangular pulse. The other test, the test number 2, is really more of a longitudinal with some component of a lateral load. So this is typically done in a sled where you attach the seat to a sled and impact on a horizontal surface. And because of this yaw angle relative to the seat, you create both a longitudinal acceleration, also a lateral acceleration. They're both triangular type of pulses, but of course the levels, duration, and the peak acceleration are somewhat different. Now, the test conditions selected for these tests, whether they're for commercial rotorcraft or for military, they are based on mishap data statistics. And those statistics have been acquired over many years. And then that just kind of defines what those test conditions should be. Now, in terms of personal flying vehicles, the data obviously doesn't quite exist yet. So you have to kind of think about what type of operational environment that you're going to operate the personal flying vehicle, what types of velocities you're flying at, what the altitudes, and what kind of worst case scenarios that may come up, and basically try to tailor a design requirement or a design condition for any kind of an occupant restraint and seating system so that you can properly protect them. The pass-fail criteria for these tests are, again, based on the occupant injury criteria that I have mentioned before, primarily HIC for the head injury criteria. In case of civil certification, lumbar spine loads, and also restraint system loads. The restraint system loads are somewhat, maybe not quite intuitive. The concern there is you don't want the restraint system loads applied to the torso or the pelvis area to be so high that you create tissue damage as you are restraining the occupant. So that's why you need to have fairly wide webbing to be able to distribute those loads evenly or as uniformly as possible on the occupant. I think I mentioned this before. Ideally, these tests are conducted using either a drop tower or a sled test facility. Test 1 is more suitable for a drop tower. Test 2 is more suitable for a sled test facility, although it is possible to do these tests, both of these tests, either in a drop tower or a sled test facility. It's not ideal, but you can configure it to be able to do it in one facility if you don't have access to both facilities. Testing is expensive, so for qualification or certification, you may have to do some testing in the end, but it's much more cost effective, and in terms of optimizing the design to do analysis, there are a variety of analytical tools to model the dynamic response of the seat, occupant, and the restraint system in a crash environment. The two tools that are most prevalent, again, both of these have come from the automotive industry, since they're so concerned about federal motor vehicle safety standards, and they do a lot of testing. So the two tools are LS-DYNA, which is an explicit fine element code that's marketed in the US, and also Matimo, which is it's a little bit more of a sophisticated tool that are really very specific to occupant dynamic analysis. LS-DYNA is more of a general purpose tool, but it does have very unique and useful features for modeling occupants as well. So in terms of, as you know, there's a variety of sizes of occupants. So how do you design, excuse me, how do you design a seat to cover the entire range? So we typically look at the largest size occupants. That's given by the 95th percentile male, and then the average is the 50th percentile male, and the lowest or the smallest population is given by what's called the 50th percentile female occupants. The reason why these are important is that if you're doing testing, the anthropometric test dummies typically come in these three sizes. There isn't really somewhere in between. So you have to design for those cases, and also when you're doing testing, there are standard dummies that are available for that. So that brings us to the airbags. And I think, as I mentioned before, I think they can be used to protect the occupants during crash impacts. Some of the experience, at least the rotorcraft experience with airbags, have been both in terms of providing internal airbags to basically restrain the occupant in place as an aid or a supplement to the restraint system. And also, as I showed on the earlier slides, you can also use restraint systems to actually decelerate the entire aircraft by placing them on the structure. So they could be mounted either on the structure around the occupant, or in some cases, they may also be deployed as part of the restraint system. So on the top figure here, you can see 3 airbags, 2 on the sides and a 1 frontal one that basically cocoons the aircraft, cocoons the occupant. And these are mounted on the aircraft, and they're inflated to keep the occupant from hitting things inside the aircraft and also not flailing very much forward. But they can also be part of the shoulder belts so that they're actually mounted on the shoulder belts. And as they inflate, they restrain the occupant, particularly the neck flailing of the occupant. So there are both types of these personal restraint airbags that have been used in the past, in addition to large-scale airbags that are used to restrain the entire aircraft. So in case of personal flying vehicles, I really think that a combination of either mounted on the tubular structure around the occupants or built into the restraint systems, or is deployed from other places on the vehicle, are going to be very, very viable as an effective way to protect occupants when you don't have very large structures or high energy landing gears that you can depend on. Now then the question is, how do we inflate the airbags? There are basically 2 technologies. One is gas generating propellants. These are very similar to the airbags that are used in cars. Basically, upon a signal, you ignite the squib that fires the propellant, which creates a gas. The other solution, particularly for airbags that are built into the restraint system, have been pressurized gas. So you don't really need a very large volume of gas for that application. So you can have a very small pressurized canister that can inflate the bags for you. And typically the gas used for that application is based on helium. Now, to really be able to effectively utilize the airbags, you need to have very precise timing during the crash impact. The timing is very important because, particularly for gas generating propellants, you have a couple of seconds to fully inflate the bag. But because of the thermodynamics, the gas, which is initially very hot, cools down very quickly. And then as it cools down, you lose the pressure in the airbags. So you really have a few seconds to inflate the bags, and then a few seconds where the bag is fully inflated and provides that cushioning effect. But after that time period, the bag starts to rapidly deflate. So that's why the timing becomes very critical, as it is in the cars. So you need to be able to sense a crash event or manually activate it at the precisely the right time and provide the level of protection. The pressurized gas is not so sensitive, so you could actually inflate the pressurized gas and it will stay inflated longer than the gas that was generated from propellants, because gas-generating propellants, as I indicated, create a hot gas. As it cools down, the pressure is rapidly reduced. So you need to test the airbags, of course, not just the inflation scheme to make sure that everything inflates, but also to validate that you are getting the required benefits. It typically requires some kind of a drop facility, although you don't have to have a very sophisticated facility. You can have short cranes or an existing structure to provide a drop test environment to validate the airbags. And also, just like for the occupant analysis, there are a variety of analytical tools that can be used to model the performance of the airbags. The figure on the right there is an external airbag application. Basically, the bags are stored in that scenario in the landing gears themselves. And upon impact with the ground, when a certain threshold on the acceleration level is exceeded, the squibs are fired and the bags start to inflate. Again, the timing here is very, very precise, has to be very precise. So right before the belly of the structure comes close to the ground, you want all of your bags to be fully inflated and to provide that cushioning effect. By the way, these bags are not just sealed bags. In the case of automotive people, they have permeable bags where it lets the gas to gradually escape. For some of these bags, you may have to have an actual vent to allow the gas to expand or escape in a controlled manner. Otherwise, you might be crushing on a waterbed, which will have an elastic response and may cause the aircraft or the occupant to rebound. So airbags are relatively complicated to design, but you may be able to find some off-the-shelf bags, primarily from the automotive industry, that may be applicable for your vehicle. So when it's all said and done, you obviously want to do a full-scale test to validate all the systems that you have built into your personal flying vehicle. And that may include some structures, that act as seats or separate seats. That may include external airbags. That would include the restraint systems and any other post-crash fire or electrocution avoidance systems you have. And that all needs to be tested on a full-scale crash test to make sure that you've integrated things properly and that they function as a system. One of the things that we've learned many times is that even if you have subsystems that have been designed to function separately, perfectly, they may not work in an optimum manner when you integrate them as an integrated system. In general, integrated systems are far more effective than federated, installing one or two safety devices that are not coupled to each other or don't take advantage of the capabilities provided by each other. So one setup that we use is a combination of a drop tower and a guide beam. So if you think about a drop tower and a guide beam held at a certain angle, we raise it up to desired height and the aircraft is pulled back. It's on rollers that can go up and down this guide rail. And when you get to a desired position, you release it from this end. The aircraft basically slides along the beam, and as it comes off the beam, it has a longitudinal velocity, and also slightly, because of the slight angle of this beam, it also has some vertical velocity. So when it comes to the end, it basically free falls, and upon impact, you have vertical velocity primarily due to this drop height plus the longitudinal velocity that you have built up as you're going through the guide rail. So this is one of many test configurations that you can come up with. The others include, you can set up some simple pendulum type of swing cables. You can rent a small crane, to raise it up to the desired height and maybe swing it from there. It all depends on, what type of personal flying vehicle that you have to deal with and how you want to be able to simulate a crash impact scenario where you want to validate and perhaps demonstrate the safety of your flying vehicle. So in concluding, I have covered a fairly wide territory there, but really, in my mind, the focus on the crash safety on the personal flying vehicle should be on the occupant in a very focused way. And I still think that seats in the restraint systems, helmets, and some kind of a deployable energy absorbing system, such as airbags, are the most suitable crashworthy systems that we have experience with and technology for that can be adapted to personal flying vehicles. Depending on the personal flying vehicle, there may be other systems that you may want to incorporate. If you have some kind of a landing device, certainly there are technologies for enhancing the energy absorption capability of the landing gears. If you have to restrain, large engines and those kind of things, we have energy absorbing structures or at least attachment fittings that can limit the loads. So those are some things that are also available, but the ones that I have listed on the second bullet, I think are the most prevalent ones that I think are suitable for personal flying vehicles. I've covered quite a bit of material here, but if you really like to learn more in terms of how to design crashworthy systems, as well as some of the technologies, I think this is the primary reference that I would recommend. It's the Aircraft Crash Survival Design Guide. It's available from the Army. That is the report number. It's been published quite a while ago, but the basic techniques are the same in terms of designing for crashworthiness. However, as you might imagine, the technology has advanced since the 1980s and 90s. So you may have to do some additional research, for example, into airbags and other devices that are, of course, much more current, as well as some of the electronics, etc., for sensing crash events and deploying the airbags and other crash safety systems. But anyway, I think this is primarily the reference that I would recommend. And based on your further reading, you might want to do additional research for the newer technologies that are not covered in that report. I think that completes my presentation.
Great, thanks. We can go ahead and jump into some questions then. So you talked a little bit about the military standard 1290A. Could you talk about what regulatory body provides certifications for that?
Well, for military aircraft or the rotorcraft in particular, every program writes what's called a procurement spec, which will then reference other specs like the 1290 for crashworthiness. There may be a spec for handling qualities, etc. So it's sort of a reference material that the program specs either directly reference or extract material from.
Great. And you talked about a seated position, but there's quite a bit of design possibility in personal flying devices. So what about things like a short seat where you're sort of in a standing position? What about other sort of pilot positions other than a standard seating position would people have to consider when thinking about safety?
Yeah, so if you don't have a standard seating position, if you're standing up and wearing a device, or if you're laying flat on the device, again, those things are not going to be suitable for a conventional seat. But what I would recommend, though, is that you still allow for some restraint capability for the occupant, and also for those non-traditional kind of configurations. That's where I think the airbags would be most helpful, because you can deploy them from a variety of places. Even if you don't have a seat, you can still provide that load limiting capability for the occupants.
Great. And you mentioned something interesting there, which was the possibility of a pilot wearing a device rather than getting into a device. Yeah, that's clearly a different, very different environment. Could you talk a little bit about things people might consider if they're thinking about that sort of configuration?
Well, if it's a wearable device, one thing you need to think about is that that wearable device has weight. And if you have a crash landing, that weight basically is going to act on the occupant, right? So in that scenario, you might think about ways of decoupling that extra wearable device from the occupant to reduce the loads on the occupant. It's very similar to other concepts we talked about, but if there is a way to decouple that large mass from the occupant, that will certainly enhance their survivability.
Great. And then as people are thinking about the GoFi development process and thinking about managing budgets as well, could you talk a little bit about when the right time and development processes to start thinking about full scale crash testing to fit into that development process?
Well, the crash testing obviously is the very last step in the process, right? After you built the system and hopefully did some flight testing, etc. But what I would do is you should start thinking about safety all along the design process. So you should think about, well, what are some of the crash impact scenarios that I might encounter, and how are we going to protect for those? So we should carry that train of thought all the way to the design process and hopefully incorporate some of these subsystems into your design. And at the end of the day, that's the final check on the capability of the system. You should do some design support development testing along the way. By the way, you don't have to set up separate tests for crash in some cases either. It may be part of another test that you're conducting, maybe part of the last step for another test that you're conducting for other reasons. So if you can leverage a variety of requirements into one test, obviously that's the most cost-effective way of doing it.
And we've had a number of GoFly Master lectures thus far about virtual design tools in terms of aerodynamics, lift modeling, propulsion, those sorts of things. Are there any useful virtual crash testing or modeling tools that people might consider as tools as part of their design process before doing physical tests?
Yeah, absolutely. I tried to sort of mention that in my lecture as well. Testing is very expensive. You have to build hardware, you have to set up tests, so those are expensive items. If you're going to certify something, that may be inevitable at the end, but along the way, you should do a lot of virtual prototypes and use some of the analytical tools that we have. I did mention LS-DYNA, which works well for occupant as well as overall system level crashworthiness simulation. There are unique tools like Madimo and others for looking at occupants. So I would take advantage of all those tools along the way to basically virtually test your product to make sure that it's meeting your objectives. And if you have to do a final test for whatever, whether it's certification or to prove that everything works, that's highly desirable, but that's the last step and probably the most expensive step.
Great. And then in closing, do you have any parting words of advice for GoFly innovators as they're on their GoFly journey?
Well, it's a very challenging project, obviously, but my advice would be, as you're looking at the performance of the system, the range and the durability, I would keep safety in mind, because when it's all said and done, people have a very high expectation regarding safety. They do not want to get into vehicles or use devices that they deem inherently unsafe. So I think that would be a good start for the entire process if you can keep safety always in mind for crash purposes and bring that along with your design. It may sound extraneous, but at the end of the day, the success or the failure of a particular configuration, one of the key items is its safety.
Great, thanks so much. And with that, I'll pass it back over to Gwen to say a few parting words.
So thank you very much, Dr. Bolukbasi. We learned a tremendous amount, and it is greatly applicable to GoFly and all of our teams as they are creating their personal flying devices. Thank you all for joining us today, and we look forward to our upcoming master lectures with you. And once again, thank you, Dr. Bolukbasi. Thank you very much.
Thank you.